more specifically, he's been tinkering with artificial intelligence, machine learning applications, and things like this, and of course trying to involve Janus in the process, so to see how you can take advantage of WebRTC and Janus specifically to leverage existing artificial intelligence and machine learning frameworks, and how we basically came up with a modular and extensible framework to that. So without further ado, let's give Paolo a big round of applause so that we can get started.
Okay. Hello, everybody. I'm Paolo. Thank you for the presentation. Big and shy full stack developer at Meetecho, and thank you for being here. In this talk, I will show you how we introduced Janus and WebRTC to the machine learning and artificial intelligence world. The first question is why? Because for us it's a very fascinating matter. We can imagine a lot of real-time applications that involves the computer vision and the sound recognition, or maybe the capability of collecting live data and deliver a broadcasted experience customized by the users at runtime. Clearly, figuring out a lot of real-time application forces us to highlight that as the number of scenarios grows, the requirements increase as well. We will face up with a lot of very different infrastructures realized for massive broadcasting or small video rooms that could have divergent constraints in matter of time and devices, and could use a very large variety of hardware and software. We don't want to put in place all these aspects from the beginning, so we relaxed all the time constraints and hardware boundaries in order to explore the results and acquire some experience of this new field that is new for us. Okay, let me be clearer about our requirements. The starting point was obviously Janus. It will take care of the WebRTC stack and the media capture. Then we have to receive the media forwarded by Janus without to any manual encoding, decoding, and so on. And we achieved this by using FFmpeg. Furthermore, we don't want to overload the client, neither in CPU load nor in bandwidth occupation. And moreover, we want to make available consistent results to all the users. For these reasons, we developed a server-side application. As I said, there is no specific application we want to realize. And taking into account the whole machine learning world, it would require too much effort. And so we prototyped something modular, capable of growing gradually together with our needs. And finally, we'd like to use a language in our comfort zone, like JavaScript. And probably TypeScript will make it easier to achieve and communicate the modularity we are looking for. The choice of a language belonging to the JavaScript family led us to use Node.js. And Node.js and FFmpeg could easily work together through Fluent FFmpeg, a library that wraps the FFmpeg command line into a JavaScript module. Okay, this is the technologies recap. Okay, let's take an overview of the whole architecture. The WebRTC client intended as the sources of our media will communicate with Janus, in detail with the Janus Video Room plugin. This plugin can forward the media provided by the clients to the following component as RTP streams. Those RTP streams will flow into a second component, which is the stream elaborator. This is the real core of the project. It receives the RTP streams, elaborates them, and finally sends the results back to a third component using an UDP channel. The third and the last component is the Janus streaming plugin, in charge to receive both the RTP streams from the Janus Video Room and the elaboration results from the stream elaborator. The streams, such as the results, will be forwarded to the WebRTC compliant receivers through media channels and media streams and data channels. Okay, let's spend a few more words on the stream elaborator's behavior and on its features. To develop a component able to apply machine learning to real-time media, we broke the elaboration flow into several steps. For each step, we identified the requirements, pitfalls, and responsibilities. Among all the tasks resulting from this analysis, the ones that could be automatized and executed under the hood have been implemented in some superclasses. Inheriting these superclasses in our project means to have out of the box a collection of structures, utilities, control flows, and everything else is needed to focus only on the specific application code. Okay, first thing first, we have to deal with both audio and video media. And so the first pitfall is to face up with the divergent kinds of customization. For example, a video stream is featured by a video codec, resolution, or its own frame rate, and so on, as well as the audio stream has its own frequency, or if it is a stereo or mono channel, and so on. Besides, we have to choose how to format and the data that will be sent to next steps. A video stream could be forwarded, for example, as a continuous stream, or maybe as a collection of ordered pictures. After the media are fully decoded and forwarded, the second step is the elaboration phase. It could be a classification, or a prediction, or a detection. This task could be completed in several ways, but all these ways can be classified into two main categories. We can execute the code locally through the usage of a library like TensorFlow or Caffe and so on, or maybe relying on third-party libraries that wraps these the aforementioned engines like Face API or OpenCV or dleap and again. The other way is to execute the elaboration remotely using an external cognitive service like the ones offered by Azure or Amazon or Google and so on. In both cases, the incoming media should be properly handled to fit the input expected by the elaboration. We have to do some kind of feature extraction or normalization and so on. Once the results of our elaboration are ready, it's necessary to handle them, either if they have to be sent back to the Janus plugin, or if we had any other usage in our mind, probably the raw results must be crafted and managed properly. Moreover, depending by the implementation, the just seen steps could present optional tasks, like bootstrap and setup phase, or maybe they could have some teardown routines. And obviously, each step should be controllable, observable, isolated, and replicable. Okay. Okay. We'll try. starting from the previous consideration, if you remember them, we can easily imagine an architecture
Not really.
of composite of nodes. Each node has its own life cycle, made of a configure, a start, a stop, and a tear down transitions. Some nodes have to forward data downstreams, and this communication between nodes are obtained through channels. If a node has an output channel, it is a producer. If a node has an input channel, it is a consumer, and the middle stage nodes have to be both consumer and producer. From another perspective, a node able to receive the RTP stream from Janus through an underlying element, let's say FFmpeg, it is a receiver. A node that have an element with the capability of sending message to Janus, for example using a UDP client, it is a sender. A node that implements any kind of inner elaboration of data, it is a module. So we can obtain more complex topologies attaching multiple nodes to the same output channel, or maybe attaching multiple output channels to a single node. For example, we have an audio input that will forward the audio byte stream to, let's say, a speech-to-text module, and a video input that pushes data to two different nodes. For example, a face detector and an age detector. Finally, the middle tier modules will forward their results to an UDP output node. Everything is flexible. We can add, for example, between the middle tier nodes and the UDP output, post-processor capable of merge the results, so we don't have any more uncorrelated data. Or maybe we can pipeline the face detector to the age detector in order to break down the CPU effort. Okay, let's start to get our hands dirty. This is the node interface that summarizes all what we have said till now. A node is identified, it describes the common parts of all the nodes. And for example, a node is identified by a unique ID, and we keep the track of its downstream nodes in a list named children. A node could be customized through a configuration object, and there are a group of methods, prepare, start, stop, and tear down, that will implement the aforementioned under the hood tasks. They will be automatically invoked by the superclasses. And finally, there are a couple of references to the controllability of the node. For example, the control channel and the true function and the controls and set controls. But I say the nodes could have different roles, so we need to expose additional interfaces, the additional interfaces we mentioned before. If a node has the output channel and the method used to write data into this channel, it is a producer, and do a speech for the consumer interface. The elaborate function is one of the most important of the whole project, because it will be triggered each time a new data become available on an input channel, and is one of the few classes that will remain abstract till the complete class. And this implementation is responsibility of the developer. Okay, let's say something more about this channel class. Channels are an extension of a transform object, and transform is a type of the node stream object intended to apply a transformation to the incoming data before they make them available to the registered listeners. They are one-way streams, and the transparent object is of type buffer. The transformation should respect the type transformation in the snippet, and subsequent transformation could share a common internal state through the ref argument. In order to deal with the node lifecycle, we said about method like start, stop, prepare, and tear down. But those are internal methods and could not be overwritten. We need some extra interfaces, module, receiver, and sender, composed by methods that could be optionally implemented by the developer and should describe how a node will use external libraries. In the model prepare, for example, we could import and load a TensorFlow model, or maybe we can import a dataset and train our model, or maybe we can do the unshaking the connection with an external service. Same is true for the other two mentioned interfaces. These methods are automatically invoked during the node lifecycle by their corresponding internal method. Sync start, source start, and module start, for example, are invoked automatically by the node start method. Okay. Now we have to create the three abstract superclasses that will be the skeleton of our project. Let's call input, output, and elaborator, mixing the interfaces described till now. All the abstract classes. It's important to notice that all these abstract classes will be injected with a configuration, an inherited configuration object, used to configure the node at runtime during its life cycle. The configuration class is another abstract class that sorry. I will do that out. To implement a configuration class, developer should simply write a JSON and map the property of a JSON on an extension of the configuration class with the methods and the properties he is looking for prepare its configuration. A static function called load configuration is provided out of the box to load the configuration dynamically in a node, and it's invoked in the superclass construction automatically. Okay, once the superclasses are defined, we can start our really project, our low-level project, implementing our application. The first thing to do is to prepare to create an input node that uses FFmpeg to receive video or audio and so on. In the source prepare, we will allocate the FFmpeg instance and configure them through a configuration object created ad hoc. For example, into the configuration, we can point to a valid SDP file for the input parameter, or maybe if we want to receive to the next nodes, forward to next nodes in a collection of JPEG picture, we can add in our configuration the format output image to pipe. When source start is invoked, the instance of FFmpeg could be directly piped to our output channel. Then we have to extend the configuration, the elaboration nodes. To extend this node, we have to wrap the chosen library to the various lifecycle phases of the node. For example, to use an external service, we can set up the connection with the external service into the model prepare function, and then write an elaborate function that will dispatch the data through an HTTP client or a socket client, depending from the service we are using. Once the results are received, they will be propagated, will be forwarded to the subsequent, to the following nodes through the propagate method. Nothing changes if we want to use a local library. In this snippet, we can see how a JPEG frame received by the video input will be used to estimate the human body pose through a pre-built TensorFlow model called PoseNet. The PoseNet model will be loaded into the model prepare, and when a new image become available, the elaborated function will convert in a tensor 3D and will use it as argument of the PoseNet method estimated single pose. When the estimation, the classification is done, results will be wrapped in a PoseNet detection object that will elide the useless information and propagated to the following method through the propagate function. Okay, when the elaboration is completed, we need to send the results back to Janus, and we can do this specializing the output node. Into the sync prepare, we will allocate a UDP socket. Into the elaborate method, we will simply use the socket to push data, to push the received data. For example, in this case, we want to avoid data truncation, and it's opportune to inject a transformation function in its input channel in order to split received data into chunks and wrap each chunks with some additional information like the fragment number, the message ID, and so on. Okay, last but not the least, we can easily coordinate all what we have done through a public API. The API object keeps tracks of all the allocated nodes and in a map, and through an internal controller could send messages to all subscripted nodes over the control channel. To create a new instance of a node, it's available a factory method. Simply by passing to this function the node type, the path to its configuration, and some extra option like an ID and the list of its upstream nodes, this method will allocate a new node wire to the right parents and invoke its prepare method. We can build a network with this few lines of code. Starting from the input nodes, we can allocate the video input node, then a PoseNet node, and we can add the video input to its parents, and finally a UDPC that will receive data from the PoseNet node. Once the network is fully defined, the API object can start all the nodes by sending a status message over the control channel. This channel is shared by all the nodes, and the recipient of this message is inside the message itself. Only the recipient will change its own status and invoke its own start method for the stop phase. Okay. Now I will show you a couple of static examples, and maybe after I will show you a demo. I'm not so confident with this demo, but probably it's not the main technical issue we can have during this talk, so I feel a bit more confident. The first example is realized using the video input node described, and a node capable of communicating with the Azure Emotion Detection service, and finally a UDP sender node. The image decoded by the input video is sent through an HTTP client to the external service. Once the result is received, it's packetized by the UDP sender, and the client is able to show results on the left column. The second example is quite similar, but this time we used a local code. We using an object detection TensorFlow pre-trained model, and the results are detection box that will be drawn on a canvas that overlaps the video at real time. Last example is a bit more complex. This time the elaborator will use an OpenCV OpenCV face recognizer called the LBPH face recognizer. Into the model prepare, we trained this model with the faces and names of the actors of Famous Friends sitcom. Then we removed the video room plugin from the scenario and the active stream to Stream elaborator and streaming plugin are provided by a GStreamer pipe directly from a static file. Let's try the demo. Yeah. He is more fun. Silent. What's next? First of all, we have to provide the capability to evaluate how the elaboration will affect the GPU, the CPU effort, and how introduced by the elaboration, and how this elaboration could ruin or boost our results. Then it should be nice to work on the video stream directly, removing the RTP stream from video room to the stream plugin. And maybe we want to prepare this kind of tool to a bit more complex machine learning scenario. Maybe implementing an online training using the control channel to dispatch rewards to the upstream nodes. We want to test with as many models as possible, maybe training our own models, and maybe wrapping, creating another superclass that will wrap the capability of implementing different languages nodes. And finally, we want to improve our API, maybe create a network dynamically feeding the API with a static configuration file, and so on. So, thank you for the interest in the listening, and thank you.
Paolo tried everything, but I think we have time for a couple of questions if you want. So, is there any question? Okay, I see you go in the back.
Hi, thanks for the presentation. Since it's a very interesting topic, and I used to play with deep speech in terms of flow, and I was wondering if you were working with voice recognition.
Yes, not with the local code, but with we use the speech-text module from Azure, and we are working on a local deep speech model in order to translate from speech to text and take the voice commands to obtain to do something specific. That's among our interest. Thank you.
Okay. So I have a question about the output of the elaborator node. I'm not sure whether it's just a metadata with the results, or also a modified stream, audio or video stream, or maybe both.
Right now, it's only metadata. If we pass a picture and do the pose estimation, we will obtain 18 landmarks of our body and use in a client to draw our stickman, my stickman. But we are really interested to work on the stream directly. So we can forward an elaborated stream to the streaming plugin and show a manipulated video at real time.
So that would be better for having synchronized video stream and metadata stream.
Yes, this is our main target because we are, as I said, we are experimenting the tool. So we, for example, for the video live demo, you can see we have a 0.5 milliseconds of delay, and probably if we work directly on the media, this could be avoided, even if the FPS should be full.
Thank you.
Any last question? I see one in the back.
How do you decode the video?
Right now, with plain FFmpeg, I have a FFmpeg configuration class, and I can show you. This is the FFmpeg configuration class, and we set the kind of media, the codec, the media rate, for example, a frame every 3 frames per second, but just for purpose we can raise this value, and how we forward a collection of pictures through the parameter image pipeline. With this, we will receive a list of pictures, a collection of ordered pictures, and in our input channel, in the following input channel, we can add a transformation function to be sure that for each buffer we receive only a single frame, and then elaborate that frame. Okay?
Well, thanks.
You're welcome.
Thank you, Paolo. Next speaker is Luca Pradovera, who is also very well known in the RTC community. He was one of the founders of Vociolingo and is now